Hi everyone. In this video, we'll discuss a special type of derivative called a directional derivative and another type of derivative called a partial derivative. We will examine these as extensions of what we saw in the previous video, which was the notion that we could take the derivative of a scalar field with respect to a particular vector. So let's begin by defining what we mean by a directional derivative and by a partial derivative. So if y is a unit vector, and when we say unit vector, we simply mean a vector whose norm is length 1, and again, for our purposes, we'll be using the standard Euclidean norm, then the derivative of f with respect to y is called the directional derivative of f at a in the direction of y. So before we move on and talk about partial derivative, right, we have here the directional derivative. If we think back to this previous definition, so we said the derivative of f with respect to y at a point A was equal to the limit as h goes to 0 of f of a plus hy minus f of a over h. And one of the things that we noticed last time was that if you had, say, two different vectors y, both of which were in the same direction but had different magnitude, then this value would actually change, right? And in fact, if y1 was 2 times y2, then the derivative with respect to y1 would be twice that of the derivative with respect to y2. So there was sort of this scaling going on with y, and so we said, well, this on its own can't really be considered a directional derivative because it doesn't just change with the direction, it changes depending on the magnitude. So what we're going to do is we're going to define the directional derivative to be a derivative with respect to a vector y, which is a unit vector. So by normalizing the length of that vector, now we really have something that as we change just the direction, we're not changing the magnitude, we just change direction, we can see how the derivative of the function changes with respect to that direction. This also has the sort of nice interpretation of being, if you're on some surface, the directional derivative is sort of telling you, so let's say I'm in R3. Okay. And let's say I have, some sort of surface, maybe it looks something like this, right? Okay. So I'm picking some point A. Here's A, and maybe that maps up here to some point on the surface. And then I pick a direction y, and now I'm standardizing this so that y is a unit vector, okay? Then really what this is doing is you can almost think about, okay, if I fixed this direction and then mapped this line up to the surface, right, I might get some sort of, who knows what this might look like when it gets mapped to the surface. But now this is really somehow like capturing the the instantaneous rate of change of the values of this function restricted to this particular line in the domain. Okay, so this really does sort of carry over our usual notion of a derivative by just standardizing that we want this y to have norm 1. Also, if you think back to just our limit definition of a derivative, in some ways, right, that was just had a f of a plus h. You can think of that h being multiplied by a 1, right, which would be in some ways the unit vector in R. But in R, there's only one unit direction, right? Well, I guess there's two, positive and negative. If you're measuring in the positive direction, right, there's just one. So this directional derivative is really actually getting a little more closely at what we might actually care to measure about the instantaneous change of a function of multiple variables. All right, so we have a derivative of a function with respect to a vector. If that vector we're taking the derivative with respect to is a unit vector, now we're going to call that a directional derivative. So that's our first definition here, is just directional derivative. right? Now, the second piece of this is now we're going to take this notion of a directional derivative and we're going to look at special cases of that. So if your vector y happens to be equal to ek, where ek is one of my standard basis vectors. So, right, if you've taken linear algebra already, or you took linear algebra previously, you may have seen this notation. Here ek, right, is just the vector whose kth entry is 1 and everything else is 0. Right? So, right. And so it depends on how many dimensions you have. If we're in R2, right, there are only two standard basis vectors, E1, and these are vectors E1, which is 1, 0, and E2, which is 0, 1. In R3, there are three standard basis vectors. But notice that each of these standard basis vectors, right, has norm 1. So these are special vectors with norm 1. And they're special because, right, they just point, if I were to sort of plot these vectors in R3, right? So if I'm in R3, these vectors are in R2. If I'm in R3, the standard basis vectors, just one of them points here, one of them points here, and one of them points here. So they just point right along the coordinate axes. Okay. So if I take a directional derivative, but now I use one of these standard basis vectors, we call this a partial derivative. Okay. Now, the partial derivatives, again, they are just special directional derivatives, but we'll actually see in a minute, right? You may recall from Calc 3, you had nice ways of calculating partial derivatives. Before we do that, I just want to note that even just for partial derivatives, there's a lot of different notation that gets thrown around. So you may see things written like d sub k of f of a. So this might be like d2 f of a. That would be the partial derivative of f with respect to the vector e2, or with respect to the second variable. You might see this sort of notation. So partial derivative of f with respect to the kth variable evaluated at a, or you may just see f sub x sub 2 of a. There's lots of different notations. And we've sort of discussed this a couple times before, that one of the things that can sometimes be the most confusing about multivariable analysis is simply there are a lot of different notations. And we'll see as we go along that sometimes one notation does have advantages over the other. But I did just want to mention you may see a number of different notations. And anytime you're confused in this course about notation, just reach out. I'm always happy to clarify because there are a lot of different notations for these things. So to make sense of this and to explore a lot of other things today, what I want to do is I want to spend the rest of this video just focusing on this function. Okay, so I want to define the function f of xy to be x times y squared divided by x squared plus y to the fourth if x and y are not both 0. And if x and y are both 0, well, obviously if x and y are both 0, this expression is undefined, so we can't use this expression. If x and y are both 0, then I would like to define this function to have the value 0. Okay, so the only function we're going to be talking about for the rest of this video is this function. Okay, and what I want to explore is what are its directional and partial derivatives? How might we compute those things? Okay. And what does that tell us about like differentiability, right? Does that tell us anything about differentiability? Now we haven't yet defined differentiability. So we're really going to be doing some exploration along the way to see what type of behaviors might be possible for a function, for this particular function. All right. So let's start. What are the partial derivatives of f? Okay. So this function f is a function, right? It takes inputs in R2. It's a scalar field, so it spits out things in R. Okay, so if I want to look at, there's really sort of two ways to think about partial derivatives. In a Calc 3 course, right? So if you took a Calc 3 course, if you took a Calc 3 course, right? So if you took a Calc 3 course, right? So if you took a Calc 3 course, right? So if you took a Calc 3 course, right? So if you took a Calc 3 course, right? So if you took a Calc 3 course, right? So if you took a Calc 3 course, right? So if you took a Calc 3 course, right? So if you took a Calc 3 course, right? So if you took a Calc 3 course, right? So if you took a Calc 3 course, right? So if you took a Calc 3 course, right? So if you took a Calc 3 course, right? So if you took a Calc 3 course, right? So if you took a Calc 3 course, right? So if you took a Calc 3 course, right? So if you took a Calc 3 course, right? So if you took a Calc 3 course, right? So if you took a Calc 3 course, right? So if you took a Calc 3 course, right? So if you took a Calc Okay. You probably would have said something like the following. Well, you're going to find the partial derivatives by, just you sort of look at this, and if you want the partial derivative with respect to x, for example, so let's say we might write this as the partial derivative of f with respect to x, evaluated xy. In our notation, we might write this as f prime evaluated at a point A with respect to the first standard basis vector. Okay, but often in a Calc 3 course, what you did is you said, well, I'm going to look at this, and I'm just going to pretend y is a constant, and x is the only variable. If I want to take a partial derivative with respect to x, that's what I do. So, okay, this is a quotient, right? So I need to use quotient rule. So the derivative would be low times the derivative of the top. So I'm pretending y is a constant. So this is a constant times x. So the derivative is just that constant. So minus high times the derivative of the bottom. Well, the derivative of the bottom, I'm pretending y is a constant. So that's just going to be 2x all over the bottom squared. Okay. Okay. And I could go about simplifying this, right? But this gives me some notion of a partial derivative, right? Yeah. Now that's fine in Calc 3, but that's not the definition we just wrote down, right? So what are we going to do in this is not 5610, this is 5620. Yeah. Well, I mean, I could write out this sort of explicitly using the limit definition, but I actually want to sort of shortcut and show that the definition we've provided actually justifies doing this. So let's say I really am trying to calculate f prime of a at e with respect to e1. Okay. So what should this be? This should be the limit as h goes to 0 of f of a plus h e1 minus f of a divided by h. Okay. Now, let me sort of convert this, right? If I think about these vectors, so let's give A some particular coordinates. Like A is just an arbitrary point. So let's imagine A is just the arbitrary point xy. And E1, right, that's just the vector 1, 0. So A plus H times E1 is just going to be x plus H, comma, y. So if I substitute that in here, right, what I get is that this is the limit as h goes to 0 of f of, now this is now the input x plus h comma y minus this is just x comma y all divided by h. And now if I look at this, I could sort of think for a minute, what if the only thing that's changing here, the y's are fixed, right? Does that sound familiar, right? Up here, we just sort of, well, the y's are fixed, right? The x is the only thing varying. Now we really can see that here, right, in this expression. And sort of more formally, you could think about just define g of x to be the function f of x, y for y fixed. So for each fixed y, you can define this function g of x. Then this expression here just becomes the limit as h goes to 0 of g of x plus h minus g of x over h, which is precisely g prime of x for each fixed y. Okay. So what we're able to do here is justify that we actually can take partial derivatives right? Simply in exactly the way we did in Calc 3 by just saying, well, just pretend the variable you're not taking a partial derivative with respect to is fixed, right? So now this doesn't have to be in the Calc 3 way and in the Math 5620 way. Now we've justified that this is just a valid way to take a partial derivative. Now, we will also point out, however, I've been played a little bit fast and loose here, right? This will not work at 0, 0, right? At 0, 0, I have to do something else, right? So here we've calculated the partial derivatives at every point x, y, except at the point 0, 0. Okay, we will actually calculate the derivative at 0, 0, but we're going to have to go back and do the limit definition to do that. We're actually going to do that together with some other directional derivatives. So let's take a look then. Let's sort of ask another question. Now that we basically see what I consider good news, which is, the Calc 3 that we did, back whenever we took Calc 3, it still works. So let's see then, what about other directional derivatives? So let's imagine now, I don't want to take just, last time I took a partial derivative with respect to x. Let's say this time I want to just take a generic directional derivative. Okay, so I'm going to just start, I'm going to imagine that I'm taking a directional derivative in the direction of a vector y, and I'm going to give it that vector y coordinates y1, y2. Okay, and it should be a unit vector, right? So y1 squared plus y2 squared should be equal to 1, although we'll see we're not going to end up making a lot of use of that particular fact, but we'll see where that comes into play in a bit. Okay. All right, so if I wanted to calculate f prime, and let's look at it particularly, let's calculate the directional derivatives now at 0, 0. So that's my point A, and I want to calculate them in the direction of this vector y1, y2. Okay, what would this be? This would be the limit as h goes to 0 of f of a plus h times y, 0, 0 plus h times y1, y2, minus f of 0, 0, all divided by h. Okay, let's see, what is that? That is limit as h goes to 0 of, okay, this quantity here is just going to become, this is going to become f of h y1, comma, h y2. F of 0, 0, that's defined to be 0, so that's going to disappear. So it's going to be this over h. Okay. Well, now this is not so bad. I could actually plug in, right? As long as y1 and y2 are not both 0, which they aren't. Why? If they were both 0, they couldn't be a unit vector. Okay. So as long as these aren't both 0, which they aren't, okay, I can use this expression here to evaluate the function. So this is going to be, I'm going to just factor this out as a 1 over h. So this will be a limit as h goes to 0 of 1 over h times, now I need this, okay? So for x, I'm going to plug in hy1, and for y, I'm going to plug in hy2. So I'm going to get an hy1 times hy2 squared divided by hy1 squared plus hy2 to the 4th. All right, let me do a little bit of algebra here. And if you need to add in another step, feel free. The limit as h goes to 0 of 1 over h times, here in the numerator, I'm going to get an h cubed, y1 times y2 squared. Here in the denominator, I'm going to get an h squared times y1 squared plus h squared y2 to the fourth. Now, one of the nice things about all of this is what happens. I have an h cubed in the numerator here, and h squared and an h. Those are all going to cancel out. And so what this is going to end up being equal to is this is going to be the limit as h goes to 0 of y1, y2 squared divided by y1 squared plus h squared y2 to the fourth. All right. Now we need to evaluate this limit, we need to break it out into two cases. Okay. If y1 is 0, okay, if y1 is 0, then what's going to happen? My numerator will always be 0. The denominator will be h squared over y2 to the fourth. So it's always, this expression will always be 0 for every non-zero value of h. This value will be 0. So the limit will be equal to 0 if y1 is equal to 0. Well, notice that, by the way, if y1 is equal to 0, this condition up here, that the vector has norm 1, forces y2 to be 1. Okay. So really, what this is doing is this is giving us the directional derivative at 0, 0 in the direction 0, 1. That's actually just the partial derivative with respect to y. Okay. Now, if y1 is not 0, okay, then what happens? Well, if y1 is not 0, then as h goes to 0, this term goes to 0, right? And so I end up with y1 over y2 squared divided by y1 squared, which simply becomes y2 squared divided by y1. Okay, a factor of y1 cancels from the numerator and denominator. And in fact, I can simplify this a little bit more using this identity here. Turns out, right, as soon as you know y1 for this vector, you know y2 because, well, you have two choices for y2, I should say. But actually, you can here use the fact that y2 squared has to be 1 minus y1 squared. So this is 1 minus y1 squared divided by y1. So you get an expression that's actually purely in terms of y1 for the directional derivative. Now, let's sort of investigate a couple of things here. Okay. Now, the first thing we can see, right, and again, this is just if I plug in 1, 0, right, if I were to plug in 1, 0, come over here, this would give me out 0. Right? Okay, so that actually shows me that my directional derivative in the x direction is 0. This shows me my partial derivative with respect to x is 0. This shows me my partial derivative with respect to y is 0. So from this, we get a couple of things. So one is the partial derivative with respect to x at 0, 0 is just 0. Partial derivative with respect to y at 0, 0 is also 0. But you could calculate a lot of other points. So let's say you wanted the derivative at 0, 0 with respect to the vector square root of 2 over 2 comma square root of 2 over 2, right? Well, you can come over here and see exactly what you'd get. In this case, because they're equal, you're actually just going to get that this quantity is equal to square root of 2 over 2. So anyway, you can calculate lots of these things, and that's perfectly fine. And that's one of the things we want to do is get comfortable with using this definition. But let me also emphasize, right, you can do this. This actually gives you a directional derivative for any direction, right? So the directional derivative exists here in every possible direction, right? So you can sort of imagine you're standing at this point, and in every direction you turn, right, you're standing on the surface in every direction you turn, right? And imagine you can only sort of look in a straight line forward and back, right? But in every direction, this is nice and differentiable, right? I turn here, it's still differentiable, right? So whatever's going on with my surface, as long as if I turn and fix a direction and I only look forward and back in that direction, right, my surface looks nice and differentiable there. Okay, so sort of nice, right? I can calculate this directional derivative in every possible direction, and certainly you can come up with functions where that kind of thing wouldn't be true, right? We've seen lots of examples in 5610 of like, what's a non-differentiable function look like, right? So they could have corners or other things going on in just that slice that you're looking forward and back in that one direction. Now, before we move on, I do want to point out that already, though, there's something a little odd going on here. Okay, let me get a little cleaner here. So in a Calc 3 course, you probably talked about directional derivatives. And one of the things that you often do with directional derivatives is you see some sort of formula for calculating them. Okay, and often sort of one of the rules you learn, and I'm obviously going to write this up, as we'll see in a second, there's something missing. Right? So one of the things you might learn is, well, if you want to calculate the derivative, essentially, if I wanted to calculate this derivative, the derivative at the point 0, 0, in the direction square root of 2 over 2, square root of 2 over 2. One of the things that sort of formulas you sometimes see is, well, okay, take the partial derivative with respect to x at 0, 0, and multiply it by the x component of the direction you're moving in. And then take the partial derivative with respect to y and multiply it by the y component of the direction you're moving in, and that'll give you the directional derivative. Well, in this case, that's 0 and that's 0. That would give me 0. Okay. So something's going on here. Either I've messed up using my limit definition of the derivative, or there's something about this formula. This is a formula you would have used in Calc 3. I'm not making up this formula, right? There's a formula you would have used, but somehow this formula is not valid for this particular example. One of those two things has to be true. Now, I'll go ahead and let you in on what is probably not a very good secret. I did not mess up on the limit definition, right? The limit definition, unless you did some algebra wrong or something, like, that's going to be right because this is the definition. So somehow there must be something about this rule that doesn't apply here, and, well, I'd probably like to figure out what it is. All right, so we'll sort of leave that as an open question, but just an observation that there's probably something a little funny going on here with this function. All right, so we observe, though, that all of the directional derivatives exist here. So this seems like a pretty nice function, right? I don't know what differentiability really means yet, but it's certainly nice, right? So let's ask another more basic question. Surely a function that's this nice, that has all of its directional derivatives, right? Is it continuous? Right? It feels like it has such nice differentiability properties, right? It must be continuous, right? So let's look at this. In particular, as you might suspect, just from the way it's written, probably 0, 0 is where I need to check things, right? Because this is a product of continuous functions in each variable, right? This is a product of continuous functions in each, or this is a sum of continuous functions in each variable. So like this feels like continuous things combined nicely. This ought to be continuous everywhere except at 0, but now I got to figure out sort of if this 0 thing, like is that filling in the hole sort of in the right way? So in order to understand that, we really need to know what is the limit as x and y go to 0, or go to 0, 0, the 0 vector, of this function f of xy. So often to just sort of gain some intuition, right, it's helpful to sometimes think along paths, right? So what if I started by looking along, say, x is equal to 0? Okay. So if x is fixed at 0, then I just need to look at a limit as y goes to 0 of, well, x is 0. Oh, so let's write this down. So I need to look at this limit, right? I fix x to be 0. Now look at along that path, let y go to 0. So this would be the limit as y goes to 0 of, well, that's going to be 0 times y squared divided by 0 squared plus y to the fourth. This numerator is always going to be 0. Okay. So, and this is for non-zero y values, this is not 0. So for all of the non-zero y values as we're approaching 0, this quantity is defined and is 0. So as y goes to 0, the limit is 0. So along that path, we get 0. We could look along y equals 0, we'd get the same thing. Look along that path. Okay. However, what happens if we look, say, along the path x is equal to y squared? Okay. So in that case, let me take a limit as y goes to 0 of f of y squared y. Okay, what is that going to be? That's going to be a limit as y goes to 0 of, now for everywhere I see x, I'm going to plug in y squared. So it's y squared times y squared over y squared squared plus y to the fourth. Well, a little bit of algebra here gives me that this is, this is y to the fourth divided by 2y to the fourth. Limit as y goes to 0 of 1/2, which is simply 1/2. So now I have a problem because those are not equal to each other, right? Well, I say I have a problem. Really, it's actually sort of nice because it tells me something, right? The limit along this path is not equal to the limit along this path. Therefore, right, if the limit existed, then the limit along every path approaching the origin would be the same. Here, since we have two paths, both of which approach the origin, but which give us different limits, this limit does not exist. Okay. And so, certainly, this function cannot be continuous at the origin at 0, 0, because the limit doesn't even exist, right? It's not that the limit exists and it just isn't equal to the function value. It's actually, there's nothing you could plug in here to make this function continuous, okay? So this actually says sort of a bad discontinuity here, right? It's not just like a simple, oh, you put the point at the wrong height. There's no point you could fill in here to make this function continuous. So this is sort of interesting because what we saw is, well, we have directional derivatives in every direction. That seems like a pretty nice bit of differentiability to have. However, that differentiability isn't even enough to force the limit to exist at the point. So we have directional derivatives defined in every direction, but the function has an essential discontinuity at that same point. Okay. Certainly, this is not the kind of thing we're really used to seeing or thinking about for functions of a single variable, right? So, as we start to think about what differentiability ought to mean, we sort of see, well, we can't have both. Differentiability implies continuity, right? That's something we saw in 5610 for functions of a single variable. Our definition of differentiability automatically implied continuity. We can't have that and our definition of differentiability just being that all of your directional derivatives exist. Okay. So we sort of have to give up on one of these. We can't have both of these, right? Because we've seen that the existence, we can have a function where all of the directional derivatives exist at a point, but it's not continuous at that point. Okay, so we can't sort of have both of these things, or we'd be able to generate a counterexample if we did. So we're going to have to give up on one of these. We would really like, right? We really want differentiability to be a criteria sort of above continuity. So we really don't want to give up on this. And actually what we're going to do is we're going to give up on this. And if we think about this, that sort of makes sense. Directional derivatives are you're just standing and you're just looking only in one direction, along one linear path. So what directional derivatives can guarantee you is that along that linear path, as things approach on that linear path, you get the same limit. But we've already seen examples of functions where the limit along every linear path exists and is the same thing. But you take some nonlinear path and now the limit doesn't exist. And that's exactly what's happening in the example we've been exploring. So we want to hang on to hopefully coming up with some definition of differentiability that gives us differentiability implies continuity. So we sort of are going to have to go back to the drawing board in terms of differentiability. And if you go back to just say Calc 1 and think about, what are some sort of meanings I attach to the notion of the derivative? So certainly there's sort of this limit definition. I would think of that as sort of an algebraic notion of the derivative, right? But if you actually think about where that came from, right, you were drawing secant lines in the hopes of approximating your function by some tangent line. Okay. Well, what would that mean for a scalar field, right? So if I had some scalar field, right, the usual way we plot that, right, is by looking at some surface. Okay. So let's say I have some surface here. That gives you some shape of a surface here. So what would it mean to think about, I want some sort of linear approximation of this thing? Well, in this case, that probably means that I would like to have some sort of, grab a slightly different color here. I'd like to have some sort of like maybe a tangent, but it's not going to be a line anymore. It's going to be a tangent plane. So what I would like is I would like to have all of those directional derivatives. I can imagine them sort of sitting here, and there's like one here and one here. But I want those to somehow, as you sort of imagine those directional derivatives going around, they carve out a plane. Okay, I want some sort of linear structure to the directional derivatives. Now, if you go back to that formula about the directional derivative that didn't seem to be working, that formula assumes linearity, a linear relationship between the directional derivatives. That's why that formula works. But in the previous example, we don't have differentiability, so we don't have any sort of linear relationship between the derivatives. That's why that formula didn't work. If you open a Calc 3 book and crack it open to wherever the stuff on directional derivatives is, it should say something like, if your function is differentiable at this point, then this formula holds. So again, differentiability has to mean something different than just the directional derivatives exist. It has to also mean that there are these linear relationships between the directional derivatives in different directions. Okay. And again, that has something to do with the function being well approximated by a tangent plane. So what we'll do in the next video is we will finally sort of answer this question of what does differentiability mean by defining something that we will call the total derivative, right? So that will help us understand when a function is actually differentiable. And then we'll also be able to use that to prove that a function that is differentiable at a point is indeed continuous at that point. Now, we'll also see that It turns out you can also prove some things about, like, if all of the partial derivatives exist and they're all continuous in some ball around a point, then you actually do get continuity. But we really just want to define differentiability on its own, such that differentiability implies continuity. And so we'll work towards that definition of a total derivative in the next video.